All right, so I'm Jerome Feist, and I would like to welcome you all to this 20 years of quantum cascade laser celebration. The idea I had when I organized this was that, you know, it's been 20 years. The quantum cascade laser is now something which is pretty well established, and it's actually nice to see, well, in some sense, where we came from and, you know, how it all happened, but also, of course, where are we going? And that's why I try to invite basically the key players, the people who brought either technology or ideas or achievements. And of course, this is in some sense a tiny bit unfair to the new people who actually are making this field so much alive. Happily, we have plenty of posters, which will be set up in the above floor, just above on the roof of that auditorium. They are really excellent, and I really encourage you to visit those during the 2 lunch breaks and also coffee breaks. Also, I would like to advertise the coming Quantum Cascade Laser School and Workshop, organized in south of Italy by Miriam Vitiello and sorry, Giacomo Scalari, and where actually, of course, you will hear more of these new things. So with that, I would like to, of course, first thank you for coming. I have people from everywhere. This is really, really nice. The invited speakers, who for many of those had long trips to come over here. Also, I would, of course, like to very much thank our financial sponsors. They all really made this thing possible. Either, I mean, you have the list on the program that is distributed, but also a few people who really did a tremendous job in making this all possible. My secretary, Erna Hug, Markus Geiser, Matthias Beck, and Giacomo Scalari. They really did a wonderful job. And with this, I would like to basically give the word to a person who is really key to this whole enterprise, because he was my thesis advisor, Franz Karl Reinhardt, who actually was also a long, long time in Bell Labs, did wonderful work in lasers and in modulators, and he will be chairing the first session.
Thank you. Thank you, Jerome, for this nice introduction. To me, as I say, this meeting is really a homecoming. Homecoming to my alma mater, that I followed in the 1950s, and then ended up as a doctorate in the 62, and directly went over to Bell Labs, and which essentially was my second home. I feel very honored, and I want to thank Jerome that he invited me for this very special occasion, because really I had the chance, and I hope most of you, of the young ones, will have the same chance that I had. Shortly after I came to Bell Labs, I was involved in a laser situation. The laser was just invented half a year, or demonstrated rather, not invented. Invented it was much before. And Rudy is sitting here, who has actually the first patent on these lasers, okay? Rudy Kazaninov, that is. Anyway, so I came to Bell Labs with the lasers. I didn't feel at ease to work on lasers, so I wanted to do something different. Then I worked on modulators, okay? So the laser is a little bit over 50 years ago. The modulators are now, this year, 50 years ago. And things have been going on. Being a device physicist, I always felt that materials preparation is a very important part of the whole thing. Physics is nice, but as one of my professors said in Zurich at the time, no matter if you can write the most intricate Hamiltonian and you cannot diagonalize it, forget it. And another professor, that was Professor Stiefel, he was an applied mathematician, he said, one calculation, no calculation. Anyway, this is sort of the framework I grew up with, and I went to Bell Labs, and there where I met with Al Cho, and we had, after Al Cho came, we had a very good collaboration over the years that actually ended up by sending Jérôme over to Al's lab. Okay, that's enough for my kind of reminiscence. I want to introduce now my dear old friend and collaborator, Al Cho, and I really feel honored to be able to do that, because Al Cho, who was born in Beijing in China, he received his BS and MS in electrical engineering from the University of Illinois in 1960 and 1964, respectively. 61, excuse me. He worked then at Goodrich High Voltage Astronautic Incorporated in Boston, Massachusetts. In 1962, TRW Space Technology Laboratory in Redondo Beach, California, from 1963 to 1965. He returned to the University of Illinois and received his PhD and joined Bell Labs in Murray Hill in 1968. He retired as a semiconductor research vice president of Bell Labs in 2002 and is now an adjunct semiconductor research vice president of Bell Labs, Alcatel-Lucent. Al has made seminal contributions to material science and physical electronics through his pioneering development of the Molecular.Beam.Epitaxy crystal growth process. As a fact is, Al made also the first patent on MBE, and his predecessor, John Arthur, who did some work in that, but he was more interested in surface physics, but Al was really wanting to do the real thing, namely to do something that you can put your hands on and work with it. And that's, I think, what Al has done extremely well. So then he worked out all the processes, and it was a very difficult time. And I want to stray off a little bit of this, because Al wanted to do something that today is sort of self-understood. He wanted to introduce a SAS to his MBE, but his director at the time said, this is too expensive, we cannot do that. And I do remember the first kind of crystals that he grew, mostly as layers that he grew, they were not all that good. The second one was mostly acceptable. The third one was very good, and if there was a fourth growth possible, then it was certainly very good. But that was not always possible. Well, anyway, so Al worked on that very diligently, very hardly. He had also a strong kind of monitor with me. You know, I said, well, come on, this I cannot use. You have to do better. Okay. Well, anyway, Al co-authored over his scientific span over 600 papers in surface physics, crystal growth, device physics, and device performance. Al holds 87 patents on crystal growth and semiconductor devices related to MBE. Al, of course, deserves and is a recipient of many, many prizes, including the US Medal of Science that was presented to him by President Clinton in 1993, the IEEE Highest Honor Medal of Honor in 1994, the Computer and Communication Prize of the C&C Foundation in Japan in 1995, the US Medal of Technology in 2005. That was presented to him by the President Bush, and his induction to the US National Inventors Hall of Fame in 2009. And he is also a co-recipient of the first Nanotechnology International Prize, Rus Nano Prize of Russia in 2009. Joe, of course, is also an academician of 6 academies, including the American Academy of Arts and Science, the US National Academy of Engineering, the US National Academy of Sciences, the Third World Academy of Science, the Academia Sinica of Taiwan, and the Chinese Academy of Sciences as a foreign member. So I hope to have you convinced that we have really a very unusual personality here that fortunately I am able to also call as my friend, who will now be the first speaker, and I hope that you give a little applause to Al for his achievements.
Let me outline this talk first. At first, I will talk about how was molecular beam epitaxy invented, and then what was the road from basic research to production. And then I will talk about why MBE is used for the growth of quantum cascade lasers. The unique opportunity for me to work for Bell Laboratories in the late 60s was that I have the freedom to do basic research, and at the same time, it's very closely coupled with manufacturing. It is a very rich, environmental rich problem place that we can have all kinds of problems to solve at that time. Now, the most important thing, besides that freedom of doing research, I think in Bell Laboratory is that the opportunity to work with most incredibly gifted and talented people, the best researchers from all over the world, and then in all different fields to work together. So in that time, as the device getting smaller and smaller, as Franz was talking about, that we need to have a crystal growth technology prepared to make thin films as thin as a few thousand angstroms. In those days, we only have liquid phase epitaxy. To grow very thin layer is difficult to control the thickness and also uniformity. So we call for a new technology to fill this area for material support. Molecular beam epitaxy was then invented in 1970, and as Franz said, Russia gave us the first international nanotechnology prize, the Rus Nano Prize, in 2009. How molecular beam epitaxy was invented? To me, to invent something is connectivity. We connect the knowledge of one technology to another knowledge B, we add together to produce a third technology, which is, in this case, MBE was invented. For me, that I first used the ion propulsion for outer space station knowledge, plus the surface physics knowledge, and then we went on to use that to grow crystals to form this new technology called molecular beam epitaxy. What did we learn from this ion propulsion work is that we learned that temperature controllers, negative feedback systems, and liquid nitrogen-cooled shrouds, heat shieldings for the diffusion cells, and low-lock sample exchange systems. For the surface physics end, we learned that how atomic absorption-desorption studies with mass spectrometers, and then high-energy electron diffraction, low-energy electron diffraction, ultra-high vacuum system, and cleaning of the substrate surfaces. These are all from the surface physics end of it. We connect these two technology knowledge together. We use it for crystal growth. Then we produce this molecular beam epitaxy. Here just shows that when I finished the master's degree, I went out to work for Ion Physics Corporation, which is the subsidiary of High Voltage Engineering in Boston area. And we did reports like ion rocket engine stations for altitude controls and station keepings. We mounted the ion engines on these 4 legs. We can rotate these stations and then changing the orbit of these stations. After I worked there for over a year, I moved to California to work for TRW, Space Technology Laboratory in Redondo Beach. And over there, I continued to do the ion emitter studies for space traveling. And in this report, I would like to show you that, for instance, one page shows how these effusion cells for cesium ion beams were made. Notice here that this is the effusion cells, and then which is the cesium ion engine effusion cells with heat shield with tandem foils around these cells. And then here is the thermocouple heater, and then feed into negative feedback systems, control the effusion cell temperature. Look at this. Here is what the MBE effusion cell look like. Look at the similarity of these effusion cells, and also using tandem foils for heat shieldings for these effusion cells. This is when I learned the cell the construction and using for the ion propulsion work applied to my design of the MBE systems. And then those cells are mounted, for instance, in operation, are completely surrounded by liquid nitrogen shroud. And then here the shutters open, closing, all controlled by computer controlled that to grow these precise layers. Now, I would like to just go back a little bit, how we first studied the absorption, desorption of atoms on solid surfaces. Again, this is the work I did in California when we tried to do the cesium ion propulsion work. What we did here, in fact, this collaboration with Haywood Shelton in California, and Dr. Shelton is a person I want to mention that most of my laboratory experience at the very beginning is completely taught by this extremely brilliant surface physics person, Haywood Shelton, taught me all these experiments. And we were using the effusion cells, molecular beams, and with a mechanical shutter. And then the beams is impinging on the substrate. The desorption of the atoms from the substrate is then measured by the quadruple mass spectrometer, and the output of that is observed on the oscilloscope. In 1962, there is no commercially available mass spectrometers, and these quadruple mass spectrometers were built by ourselves. And then the typical trace we saw when we open and close the shutter in that experiment, you see, open the shutter, we see the exponential increase in the signal, and then saturating in the equilibrium time because the absorption and desorption beams are equal to the same. And then when we close the shutter, we had desorption from the surface, and then getting equilibrium. This shaded area means the equilibrium surface coverage of atoms on the surface at that temperature. With that, we plot the logarithm, the semi-log plot, the logarithm of time as a function of temperature, 1,000 over degree K. This is a so-called Arrhenius equation plot. With that, we can find the activation energy and with different elements. In this particular case, it's brilliant evaporative lifetime measurement as a function of the substrate temperature and the different conditions of the substrate. And in fact, this work, this element, beryllium, was first used by Mark Elegans, who was also in this audience, for the demonstration of MBE, very important p-type dopant for gallium arsenide in 1975. As I mentioned, Franz mentioned earlier, I went back to the University of Illinois in 1965, try to complete my degree, because my advisor came to California and says, if I don't get back to the university, I'm out. So I stopped abruptly from TRW, went back to University of Illinois to complete my PhD degree. And in my thesis, I completed this experiment I was doing in California. I wrote my thesis. In there, I defined the condensation coefficient. In surface physics, at that time, we called sticking coefficient, equal to S 1 minus A over B, where A is when we open the shutter of the molecular beams, the abrupt changing in the magnitude of measurement, and then go through exponential equilibrium section. And then when we close the mechanical shutter and then reverse the structure. What I define is that at sticking coefficient equal to 1 minus A over B, let's look at the extreme case. If we open the shutter, A equal to B, and that means that sticking coefficient equal to 1 minus 1 equals 0. There is no condensation coefficient, 0 equal to 0. But at the other extreme, if we open the shutter, exponential curve starting immediately, A equal to 0, then that means the sticking coefficient equal to unity. With that technique, John Arthur, in 1969, published the most definitive paper. The most MBE is rely on this result, that showing when he was using this technique to study the adsorption-desorption of arsenic atom on gallium arsenide surface. When he opened and closing the shutter, notice here, this is the magnitude A, and then this magnitude is B, and then when you open, closing shutter of arsenic onto gallium arsenide surface, you see this piece characteristics like this. But the important point is, when he turned on the gallium beam on the gallium arsenide surface, notice here, when he opened the mechanical shutter, instantly that exponential curve started. The magnitude of A equals to 0. Therefore, arsenic has unity sticking coefficient on gallium arsenide surface if the surface is covered with gallium. So why MBE rely on this so important? That is, the growth rate of gallium arsenide is only depending on the arrival rate of gallium. If you can plaster on the surface with all the arsenic you want to, only when the arsenic can find the gallium atom on the surface, it will stay on the surface. And any arsenic, excess arsenic, just simply bouncing on the surface with 0 sticking coefficient. So later on, in Redhill Phillips, in England, that Tom Foxton and Bruce George in 1977 also repeat the experiment, study the sticking coefficient of arsenic as a function of gallium beam arriving on the surface. Notice here he also find as gallium atom flux on surface getting more and more, the arsenic sticking coefficient also getting increased and reaching a plateau of 1-to-1 ratio. So this is how the MBE started with this surface physics study, the surface kinetic studies of atoms bouncing on gallium arsenide surfaces. But at that time, as I mentioned, working in Bell Laboratories, we not only one eye is doing fundamental research, we also have one eye look at what can we do with this, and can we make real devices. My interest is to more tend into to develop this technology into a useful crystal growth for devices where we can all benefit using in the future. So in 1970, I started to build the first a large MBE chamber here with stainless steel, with liquid nitrogen cool shell, and these diffusion cells I showed you earlier, I learned from these ion propulsion work. And here's me at the younger days, and then my technician at that time is Charlie Radice. And this just cartoon shows that we try to grow atom layer by atom layer with controlled different elements with diffusion cells with shutters open and closed. And this is the schematics looking down from the top of the MBE system, the stainless steel chamber pumped by ultra vacuum, and then the blue area shows the liquid nitrogen-cooled shroud surrounding the whole chamber to give us a very ultra-high vacuum. And then these are the diffusion cells. Sample is mounted in the center, rotating continuously, give us the uniformity we need. And the thing I want to point out here is this. I introduced in situ monitoring tools called high-energy electron diffraction system. The electron beam impinging on the substrate surface during growth with a grazing angle, and then the diffracted electrons is projected onto this fluorescent screen here. We look at the diffraction patterns of the surface. So we can look at the surface before we grow, how we dissolve the oxide from the surface, and during growth, and then after the growth. So what we see in this diffraction pattern is showing here. On the left-hand side, these are the diffraction patterns. On the right-hand side is the corresponding surface, looking at this electron micrograph, how the surface looked like. I wanted to show you here at the beginning, after as desorption of the oxide from the surface before, at the beginning is amorphous oxide on there. After desorbed amorphous oxide, we see spot diffractions. And the surface of that surface is matted after chemical etching and heating, and forming microfaceted surface. And the electron beam, as I mentioned, with the grazing angle on the surface, the electron beam had to penetrate through the protuberances of the microfaceting surfaces, and then three-dimensional Laue condition had to be satisfied. At that time, there was spots. Therefore, you get spot diffractions. As we grow on the surface, we're forming larger, smoother areas and forming atomically smooth with MBE growth. You see here the diffraction pattern becomes streaked. Why it becomes streaked? Because the electron diffraction now go from three-dimensional to two-dimensional, because it's grazing angle that didn't have these protuberance surfaces of hills and valleys anymore. Therefore, we got two-dimensional electron diffraction. In the two-dimensional electron diffraction is reciprocal rods. The ionosphere intersected reciprocal rods give us these streak patterns. Furthermore, I want to show you here, notice after diffraction getting smoother here become rods, we see a 1/2 order diffraction showing up. What is the 1/2 order is about? It's because the MBE further can see the surface atom, the reconstruction of the surface atom. They're 2 times larger in this particular case is 110 direction, larger than the bulk diffraction. In the reciprocal space, the 2 times larger is 1/2 order. So we have 1/2 order diffraction. I also want to point it out. We have heard MBE is growing atom layers by atom layers. And here I want to demonstrate to you it really is growing atom layers by atom layers. Notice here in the electron diffraction, we have one spot here. This spot is called the specularly reflected electron beams on the surface. Now, we use that. The surface studies the counting atom layer by atom layer with a reflection, high-energy electron diffraction, intensity oscillation. The spot I just showed you earlier, it oscillates in different intensities as we grow. And every oscillation means one atom layer is grown. And how it was happening here? If you have an atomically smooth surface, the reflected beam at that spot have a very high intensity. As we grow on the surface, of course, they start to form different islands from the surface at the beginning before the islands are coalesced into a complete smooth surface. The highest islands in density is, of course, is at 1/2 order point, had the most island on there. And then when you get in 3/4, more and more coalesce together, forming smoother areas. Finally, a complete layer is formed. Again, this is as smooth as beginning, so the intensity of this beam is getting back to the maximum again. Notice here, beautiful intensity oscillation reported by Sadowski and Lyon University. This is pointing the specularly reflected intensity, that spot, as a function of time in seconds. Notice here, beautifully, layer by layer, that is grown by the MBE technology. In this case, is the oscillation of the gallium manganese arsenide magnetic film grown at Lyon University. And I also demonstrate here, we grow, let's say, 3 atom layers of gallium arsenide, 3 atom layers of aluminum arsenide, and then get back to 20 monolayers of gallium arsenide. What we see here, because of the growth of gallium arsenide is faster than aluminum arsenide, because our aluminum evaporation rate is a little less than gallium. So when we open the shutter of gallium arsenide growth, you see here with less time to grow 3 atom layers than the aluminum arsenide layer grows, and then back to 20 layers of gallium arsenide. Indeed, we start to demonstrate that MBE is growing atom layer by atom layer with a precise control of the layer thickness. That here shows the superlattice first proposal by Isaki and Ray Zhu. The negative differential conductivity is in the superlattice open a new dimension for what was not possible in bulk semiconductor appeared to become possible in superlattice. We then, therefore, quickly try to demonstrate MBE can make these superlattice structures. In 1971, I published the first paper on the demonstration of MBE growth of superlattice structures. And with superlattice structures, of course, we all know there are 3 different kinds of alignment. For instance, you have the type 1 alignment of gallium arsenide, aluminum gallium arsenide, where electrons and holes are confined in the low bandgap layer in the same material, same layer. And then the type 2 is like in antimonide compounds, that the electrons and holes are confined in 2 different separate layers. And then finally, the type 3 is the electron and hole are mixed, that is in the superlattice structure of indium arsenide of gallium antimonide. Franz mentioned a little bit earlier, in developing MBE is not all that easy. When I first tried to compete with MBE with liquid phase epitaxy, I fell on my face, of course. I grew some layers and gave it to Franz to look at, and don't even have any light coming out. And so Franz Reinhardt is a very good scientist, engineer. He said, well, let's first do some easier work like waveguides or majority carrier devices. Let's not fool around with minority carrier device. So like making the hyperabrupt varactors, demonstrate MBE can have the continuous doping concentration changes in a very controlled way. And then, of course, in this particular, I just take one of the many papers I collaborate with Franz that's showing the growth of 3-dimensional dielectric waveguide for integrated optics with Molecular.Beam.Epitaxy in 1972. And then with the mass growth, we grow a core of gallium arsenide surrounded by aluminum gallium arsenide, and as an integrated optics waveguides grown in the layer. I continue to work hard, try to make the grown material will have less traps, less these impurities in the aluminum gallium arsenide layers, with continuous look at from how we to make the system cleaner. And we, by the time of 1976, in collaboration with Dick Dixon and Craig Casey, we made the first continuous room temperature operation of gallium arsenide, aluminum gallium arsenide, double hadron injection lasers. And that was the encouragement to me that if we work hard enough, we can finally achieve to me earlier looked like impossible. We further developed from gallium arsenide, aluminum gallium arsenide, extending to grow the indium phosphide substrate, because at that time, a lot of these devices are going to indium phosphide and making 1.3 micron device for communication systems and so on. So we got pressure to grow on indium phosphide substrate. So we had to make indium gallium or aluminum arsenide lattice matching to indium phosphide, and which is a little harder for me to handle this kind of material. And we have very lucky to have Norman K.Y. Shan visiting scientists in my lab to start the lattice match condition for growth of indium gallium arsenide epitaxial layer on indium phosphide substrate. Indium phosphide substrate had a lattice constant is about 5.87. There you can see the plotting here, the lattice mismatch in percentage as a function of indium arsenide mole fraction in the indium gallium arsenide material. We had to be precisely have the 53% of indium and 47% of gallium being in the MBE system to be perfectly matching to grow the indium gallium arsenide on indium phosphide substrate. So this material is used in most of our quantum cascade lasers for 2 to 12 micron range we demonstrated later on. So, and that's what the beginning in the 1981, we try to learn how to grow this material for this device. And of course, Norman Chan demonstrated, indeed, with MBE, with precise computer control shutters, we were able to grow layers perfectly matching with indium phosphide substrate. Fast forward, I want to show you some of the more recent results of MBE development. This is presented just 3 months ago in Canada, the North American MBE conference, by a person that Skip Wisky from Poland. Extremely outstanding work. He showed that the aluminum gallium nitride cladding-free continuous wave operation of gallium nitride lasers by plasma-assisted MBE system. He showed that the schematic, the photomicrograph, look at the precise and uniform, good interface of the quantum well structures grown by MBE for these nitride lasers. Here, I just want to demonstrate the difference of with aluminum gallium nitride cladding and then without the aluminum gallium nitride cladding. And then here is this far field pattern with and then without. He finds that with this structure here, he has no ripple in the far field. And the lasing of this extremely outstanding low threshold and then 430 nanometer wavelengths. He also demonstrated a little longer wavelengths, 480 nanometer wavelengths of the lasers with output power 220 milliwatt CW operation, and then with a very high nitrogen flux, we were able to grow with MBE 2 micron per hour. I also want to mention another very nice development is the growth of antimonide material by George Turner from the Lincoln Laboratories, also in the same conference. He grew the indium gallium arsenide antimonide, aluminum gallium arsenide antimonide quantum well rich waveguide lasers, lasing at about 2 micron range. Also, he mounted on the 9-element tapered 2 micron lasers with a micro array lens to have in the C package have a multi-watt output for these 2 micron lasers. A good result, he reported that lasing at room temperature CW, and then with a threshold current as low as 50 amp per centimeter square, very high T sub 0 at 80 K, and with multi-watt output. And of course, as we know, when we go higher wavelengths from 2 microns to 3 microns and up, in this antimonide system, we run into this problem like we had to have a thicker cladding layers and higher resistance, and then that heating out the substrate and Auger recombination problems. And therefore, when we go higher wavelengths above 4 microns, we would like to grow quantum cascade lasers for that wavelength regime. I also like to mention just a little bit about another new development in MBE is to grow single crystal metal films on gallium arsenide or 3,5 compounds. This is first demonstrated in the early days of 1978, the growth of single crystal aluminum films by MBE on gallium arsenide. And then we made micro Schottky diodes, single crystal Schottky diodes, with a 2 micron in diameter here, demonstrated with the lowest noise temperature for such device, actually used in home Delft with Bob and Arnold Penzias for the exploration, look at the skies for the Big Bang experiment. And with that, I want to say, Molecular Beam, for the basic research contribution, we have grown very high quality semiconducting materials, and then Horst Stromer and Dan Cui discovered the fractional quantum Hall effect, and then the growth of superstructures with metal layers. Ferd and Grenberg discovered the giant magnetoresistance, and the Nobel Prize were awarded for both of these discoveries. I would like to say how we finally try to reach my dream of developing MBE to production. As we know, in the crystal growth area, anybody can start grow a crystal and look at the surface morphologies, and then you can publish paper. Therefore, this is the first step. We can look at the surface morphology and then do some measurement and then publish. And then the next thing is harder, is to look at the transport properties. And if you have trap in there, the mobility is not high. So you have to make the layer getting a little better to have the high mobility materials. Furthermore, next step higher is to look at the minority carrier devices. Then you go and look at the photoluminescent. All these things is another degree of higher. Then look at the majority carrier device. And then you had to learn how to make p-n junctions, and then you start to make devices. Making devices still not finished. That you had to realize you had to make a device which will last a long time, not just burn in 1 hour, you publish paper and finish. In Bell Laboratories, we're connected to manufacturing. You had to make these devices to last for 20 years so that you had the reliability. And after I finally make that high reliability, make a laser have a long life and all that, and the next thing they come in and says, what's the cost? And you can make a laser that costs $2,000. Nobody was going to buy it for you. So you had to make cost effective. I realized that how you can make it cost effective. The cost effective, you have to make, to reduce the cost, you have to have large volume of production. So I had to try to convince how I can convince the MBE equipment company to make first production system. So as I mentioned, that we not only have to have reliability, we have to cost effective, and then I went to several of these manufacturing MBE companies. I said, well, can you make a mass production system? I have the design. I can tell you what we need. We need to have a system that somebody go in there, push the button, and the other side spitting out a wafer is or it can be sold on the market. So that's how the dream of making mass production is all about. It's not have to have a PhD and then look at this, then take a long time to make one wafer. That's not good. You have to make it so that it becomes so simple. I can find somebody on the street and train him 2 weeks and then to grow the materials. That's how you can make it successful. So then the company person, the president legitimately asked me the question, what do you think if I spend all the time making all these big machine monsters, what is it for? I was extending my imagination, and I said, wow. At that time, in 1980s, the highest production is the red laser using for the compact disc players, and each compact disc player we have a readout in there. So I said, 1 million lasers. And then so what else? At that time we have the modulation dope transistors and make high mobility devices, high speed devices. I said 1 million modulation dope transistors. And he went back to back envelope calculation. Oh, we will need one MBE production system for the whole world. What do you think? You want me to invest all the money to sell one system? And I was like, this is going to be hard. And it is extremely a big barrier for me to overcome. I had to convince him that some of the futures we cannot really predict. But if we can make it low cost, high yield, high quality devices, we'll find ways to use it. So with pressure and persuasion, and I finally convinced Revere make the first MBE production system. That was in 1988. In 1988, make this first production system. You see, huge. And then there's cassettes here. You can mount these patterns into the cassette. The automation was all go from the cassette to cassette into the growth chamber. And at that time, the MBE 6000 that can mount 4 6-inch wafer in one platen. And then the next generation is 7000 that one can actually mount 7 6-inch wafer on one platen. And then 25 3-inch wafer on each platen. And of course, we had to have what's performance, not only just how you can make it big. And the uniformity of the MBE production system is very uniform, plus or minus that 0.5% over the whole wafer. And then you can see that most importantly, high throughput, 94% operating, run 6 to 9 months without opening the MBE system for refilling. And it runs 7 days a week, 24 hours a day. And then you don't have to open the system for 6 to 9 months. And with this large production, and most importantly, the switching time from one platen to the next platen is all automated by computer control, that only 2 minutes time for platen exchange. So, continue that system here now in RF micro device. IQE now bought part of the system in North Carolina, the headquarters. Here is MBE fabrication lab. In this lab, there are more than 20 MBE production MBE systems. And then they produce that over 500 million chips per year for cell phone operations. Okay, now I would like to get into the real business here. Super lattice lasers, which led into the quantum cascade laser. The super lattice laser was first proposed by Rudy Kazarinoff and Robert Sulis, and it published in 1971. And later on have some more detailed proposals for the lasers from Capasso and Kostowski. And the thing I want to say here is the birth of quantum cascade laser. And before 1994, we have grown a lot of these wafers try to make this laser superlattice structure to lathe, but not until 1994, Jerome came to Bell Laboratories. He first studied a lot of wafers that look at the intersub-band scattering rate and carrier lifetime. And then at one point, I thought, oh, I got another Franz Reinhardt in my lab. Because when I'm working with Franz Reinhardt, it's kind of so detailed in every detail things, and I have to try so hard to satisfy Franz Reinhardt's requirement. Here now comes his student, Jerome Face, is doing the same thing to me. And of course, that was the reason that they spent that much time to study the carrier concentration, scattering time, and all these things. When he finally, and I almost gave up with him, and he finally get to design the quantum cascade laser. And amazing to me, the first structure he designed, it lathes. It was like 1994, night, 10 o'clock at night. He called me in the lab. All I can hear from the other end is, it lays. So we were so excited that night. Here now, that's why we're celebrating today, for it was 20 years ago. And of course, the structure is very complicated. What Jerome designed, there are waveguide claddings on both sides, and then the middle is waveguide core. In the waveguide core, there's an active layer. The active region also have the quantum wells and the digital grading area. And that you had to repeat another 25 times. There's hundreds of layers together. It just is almost think about impossible. And of course, the structure, you can see the demonstrating on MBE growth of these structures, and the reproducibility, control of layer thickness. Some of these layers only a few atom layer thickness, that we are able to fulfill what Jerome is asking for. Now, of course, the first announcement of that structure, you can see that Jerome published here, that what he did is he added to the regular supercluster structures adjacent 28 angstroms of quantum wells. As we know, he tried to make it population inversion. That means the final state had to be 0. And this design of this quantum well adjacent to that is that the overlap of wave functions, therefore the optical phonon nearly 0 momentum transfer, and then the compare with the transition, the relaxation time of the 3 to 2 is something like in the order of 4.3 picosecond, and then the final state here, the relaxation time is only about 0.6 picosecond, and that's what produced the population inversion and to make the lace for the first time. So this is a team. The team here now, Federico Passo, and me here, and then Al Hutchinson is the lab assistant of Capassos, and then my lab assistant, Debbie Sifko, and both of them are here today, and then Jerome Faith and Carlos Satira. These are the original team for make that quantum cascade laser to work. And also I would like to mention that Claire Mackel collaborated with me. She's probably the hardest worker I have ever collaborated with, and then Federico Capasso is the longest collaborator I have in Bell Labs for that time. That we also have Charlie Radiz and Debbie Sifko are my most important lab assistants. Without them, I would not be able to develop MBE. I also would like to mention in this audience here that Li Aizhen from China, she is the first MBE person in 1982, started the MBE in China, and she is also the first MBE person working on quantum cascade lasers in China. In summary, MBE is broadly used today for the advanced nano multi-layer crystal growth and has led to radically new devices, including quantum cascade lasers, high-speed transistors, microwave devices, multi-junction solar cells, laser diode detectors. And the disk players and the CD-ROMs are all made by MBE material. And of course, I showed you earlier that most of the RF switches and power amplifiers for our everyday cell phones are also made by MBE. I was fortunate to work with many outstanding scientists and engineers. Many of them are here in this audience today. When I think back of my career, the most important thing, the most important aspect in my life here is to work with a team. The most capable people with mutual respect and mutual trust of each other for my fellow researchers and collaborators. And of course, you have to be yourself. You have to make your work like a fun place to work. And then there has to be a purpose, a goal, and you have to keep trying until you succeed. And here is the team that, and then we were all trying very hard for Jerome Faith to make the first quantum cascade laser to work. Thank you very much for inviting me here.
Thanks very much, Al, for this very interesting and nice talk. You couldn't have done better, I'm sure. Now we have some questions. I would invite the audience to pose a few. Well, this is embarrassing. There must be questions. If there are no questions, oh, there in the back. Okay.
Yes, before the quantum cascade laser, we probably grown about, I think, maybe 200 layers. And even I remember before we computer control the layer structure, I have Charlie Redis in my lab, have a very good hand, manual, open, close 200 times for open and close, making the multi-layer structures. And of course, Debbie Sifko in the audience here, she is also very good, precise in using these mechanical earlier days with the manual control of the shutters.
Okay. Next question. Well.
How long did it last?
Oh, that's a nasty question.
I will answer that.
But I want to tell you that laser I show in the nitride laser was 2,000 hours and above. They have tested the nitride laser. And then, of course, the MBE gamma laser, all in the thousands of layers, hours, because all these red lasers in your compact disc players are made by MBE. And if you turn on your music, turn out after one music, you will not be very happy.
One more question, yeah? Oh, now we are coming. Okay, that's good, okay. First, you, yeah.
You developed MBE and parallelly afterwards, MOCVD also came parallelly and competing technology. And what was your reaction and how did you embrace them?
Yes. MOCVD and MBE are, I think, is complementary each other. In fact, MOCVD, the major player are Russ Dupuy and Dan Depka were my classmates in University of Illinois. So we were very good friends, and we have a lot of cross mutual respect and also a lot of cross information between us. And I think MOCVD is, for a lot of people earlier, in the beginning was in Rockwell in California, when Russ Dupuy there developed that to become production. And there was most people think about, there's a MOCVD, chemical vapor deposition. The mind in most of managers, chemical vapor deposition is for mass production. And then MBE in the early days already planning the manager's mind is research equipment. So for production, a lot of them, they all just jump into MOCVD. But on the other hand, the growth rate, MOCVD is faster, and MBE is now catching up. Of course, most of the devices are thinner layers now, is more favored to MBE growth for the control layer thickness. You don't need to have very high growth rate. That also another thing is MOCVD that, as you know, at least earlier days, that most of the raw materials were coming out of the chimney. They only use a very small percentage of the raw materials to deposit. MBE is more efficient using the raw materials deposited on the epitaxial layer for large production systems. And another thing is I showed you earlier, the MBE production system take only 2 minutes for transfer for one platen to the next platen. It's also faster than most of the MOCVD in transfer in wafers. So these are sort of complementary depending on what material, what device you're making. And I think that on the other hand, in the exploratory end, MBE is easier because you can have all different elements in your hand, what you want to mixing in this material, in this final device. So you don't need to rely on they have the right compound for the decomposition for the MOCVD growth. So you can change the materials more easily with MBE for the exploratory end. Therefore, most of the invention, new devices, new testings were starting with MBE, and a lot of them finally become MOCVD for production. But MBE is trying to make also production, as I show you.
There was one more question there.
I think we're continuous to develop. As you see, the next generation for large volumes, I can see for the multi-junction solar cells is one of the applications. The MBE is also very much in play. Now the highest efficiency, 43-44% of efficiency, the multi-junction solar cells are made by MBE. So you can see if you have a very efficient using of materials, if you are really using for solar cells, then you really want to make sure that we do not exhaust the big percentage of the raw material went out of the chimney. So the thing is that MBE play a very important role in the multi-junction concentrated lens that you only need small substrate with a concentrating lens for the production of 44% efficiency of the solar conversion. I think that's another one new dimension of development.
Well, thanks again, and let's give a hand to Al.